Okay, so last time we proved this preliminary fact right before we wanted to get to fundamental theorem of arithmetic, which is actually going to be the main thing that the fundamental theorem of arithmetic uh, follows from. So the theorem in question is this one. So it's that if you have a prime dividing product of a and b, then it's got to divide one of them. Okay, so a and b are integers. P divides a times b, then p divides a or p divides b. So a corollary of that was the following. I didn't box this in. So using induction, if I have a prime p dividing a list of integers here, then it has to divide one of them. Okay, so it turns out this fact is actually pretty much the thing that's going to get us prime factorization. And so this corollary was a direct corollary of this theorem, and this theorem essentially followed immediately once you had this fact from the Euclidean algorithm that you could express the GCD as linear combination of the numbers in question. So if you want to trace all that all the way back, unique factorization is a more or less direct consequence of this fact coming from the Euclidean algorithm that you can express the GCD of A and B as a linear combination of A and B. So that's the way to distill it down to kind of its base elements. Anyway, okay, so now it's time to actually apply that and prove the fundamental theorem of arithmetic. So fundamental theorem of arithmetic, stated as it is, this is I guess depending on, so of course fundamental theorem of calculus everyone knows. Fundamental theorem of algebra is another one of these fundamental theorems. So fundamental theorem of algebra is a statement about, so I mean, depending on how you want to state it, it's a statement about roots of polynomials, or maybe I should go ahead and say that it's a statement about, say, the complex numbers being algebraically closed, meaning that forming a polynomial with complex coefficients, you're always guaranteed complex roots. There's no extra stuff you got to add. So, for instance, it's not true about the reals. If you look at the reals, you can form, of course, a polynomial even just having integer coefficients and not get real roots. But for the complex numbers, that isn't true. So that's one way of saying it, right? Together with an even better statement that if you're looking, so over the complex numbers, any polynomial is going to totally factor into linear factors, and the degree of the polynomial tells you exactly how many of those factors you get counting with multiplicity. So degree in polynomial has in roots counting with multiplicity. That's kind of like a convoluted way of saying it. That's the fundamental theorem of algebra. So you might have known that fact even if you didn't see it stated in that way. So what's fundamental theorem of arithmetic? It's the statement that every integer n greater than 1 can be uniquely written as a prime or a product of primes. So it's an existence and uniqueness theorem. The existence part is the assertion that it can that any integer greater than 1 can be written as a product of primes. The uniqueness part is that it can only be written as a product of primes in a single way. Okay, up to, of course, a reordering of the primes. We don't care about that. So the fundamental theorem of arithmetic. All right, so this says that every integer n greater than 1 can be uniquely written, and that is a very important bit, as a prime or product of primes. All right. Okay, so let's prove the existence bit first. So existence, i.e., that every integer n greater than 1 can be written as a product of primes. Okay. All right. So this subproof of this part goes as follows. So suppose that there exists some integer. I'm not even going to name it. I'm just going to say that suppose that there exists some integer greater than 1 that cannot be written as a product of primes. And in order to rule out the other thing that could happen, that it's prime itself, we can also assume and is not itself prime. Okay. i.e. is a long-winded way of saying if I form the set big S that consists of integers n greater than 1 such that n is not prime and n cannot be written as a product of primes. Probably already know what's coming. Well, what kind of set is this? So by this supposition, since I'm obviously proceeding by contradiction here, this assertion here that I've made means that S is non-empty. So S is non-empty by above assumption. And S consists, it consists of integers greater than 1, so it consists of positive integers, right? It consists of positive integers. Like I said, in fact, they're all bigger than 1. Okay, so you got a non-empty set, it consists of positive integers. There exists a smallest such element, right? So S has a smallest element, say S, or little s, by the well-ordering principle. So this is, by my count, I think that's the third time I've used the well-ordering principle in a proof so far this semester. So if you need a quick refresher on that, as I mentioned before, this is in one of the appendices. It might be the first one. I think it's in Appendix A. Okay. All right, so S has a smallest element. We'll call it little s, right? So, little s must be composite. That's, what am I doing here? Composite. Yes, I can spell. So then S must be composite. Why? Well, any element here can't be prime. So necessarily S must be composite. So say S is equal to A times B for integers A and B, where A and B are integers, and these are non-trivial factors. Okay. All right. Now, we want to make use of the fact that I've said that this little s is the smallest element of my set, big S. So, looking at this, I have S factorable as A times B. A and B are integers. Necessarily, they're both strictly smaller than S. So they're smaller than the smallest element in big S, which means they can't possibly belong to big S. And if they don't belong to big S, then they can be written as a product of primes. Right? Thus, A and B are products of primes. Since neither can belong to big S, since they are smaller than little s. Okay. Thus, little s, which is A times B. A is a product of primes, B is a product of primes. So S is A times B. That has to be a product of primes. But little s is in big S, so it's not supposed to be a product of primes. So this is a contradiction, and that's it. Okay. For this little subpart, right, the existence. Now you might say, hold on for a second. I went from this step to assuming that A and B are products of primes. Since they don't belong to S, everything seems good. But you might say, wait, maybe they're not products of primes. What if they're both primes themselves, right? That's the other possibility, right? Because big S excludes primes as well. Well, if one or both of them are just primes, so they're not products of primes, then A times B is still a product of primes because A and B would be both prime. And if one of them is a prime, then one's a prime and one's a product of primes, so their product is still a product of primes. So you're good in any case, right? Okay. So we're almost done with fundamental theorem of arithmetic. We need to show the uniqueness bit. That is, we need to show that this expression as product of primes can only happen in one way, right? And in a way, this is really the most important part of this theorem. So proof is continuing here. So this is uniqueness. So I want to show that this expression as product of primes can only happen in a single way. So typical, just normal way of dealing with this when you're writing a proof is to assume not, right? Assume that you have an expression that shows, two different ways of writing this, and then show that, oh, actually these expressions are equivalent, right? They're the same. They're the same expression, so really this can't happen. Okay, and as I mentioned, this is going to rely on that theorem and its corollary that we proved at the end of lecture last time. So suppose that there is some integer that can be written as a product of primes in more than one way. Right. Again, using shortcut here. Let's say that we just pick the smallest one of these, right? So let n be the smallest such integer. Oh, I guess I didn't actually give a statement of uniqueness here. I'm not gonna spend my time rewriting it. I just went straight into the proof. Maybe I should at least write proof here so that, but I didn't keep with my format, right? My format of the previous thing was I actually wrote out what existence meant for that part. I didn't do that here. It's okay. I'm just gonna keep going. So let n be smallest such integer, i.e. Let's say n is expressible as a product of primes. Maybe there's some repetition here. I'm just saying that here's product of primes. And also, it can be written as a product of some other primes. Again, maybe there's repetition. Use S here. Yeah. Okay. All right. All right, where P sub I, Q sub J are primes. Okay. Now, what to do? Well, note, and of course, what is going to follow here? It doesn't have to be exactly this statement, but it's not going to make a difference which subscript I pick to work with here. So note, P sub 1 divides the left-hand side. What I'm calling the left-hand side is this product here. So P sub 1 divides the left-hand side. It divides the left-hand side because it's just one of the primes in the list, right? I.e., it must divide the right-hand side as well. But what does it mean to divide the right-hand side? I.e., rewriting that, P sub 1 divides this product. So now you see what's going to happen here. Okay, so this means that P sub 1 divides Q sub I for some I. Where does that come from? Well, it comes exactly from this corollary from last time, that if you have a prime dividing a product, then it divides something in the product, right? So P divides this product of integers, divides one of them, right? So here we have P sub 1 dividing a product of integers, so it has to divide one of them. Of course, this is a more special thing because it's dividing a product of integers, but each of those integers is actually prime. Okay, which is what's going to be nice here. Now, just to keep this going smoothly, we say I equals 1 after rearranging. What do I mean by that? Well, I don't care about the order of these primes, right? So when I talk about uniqueness, this is uniqueness up to reordering the primes. We really don't care about that at all. So what I would do is say this P sub 1 divided Q sub 4 in this list, right? Then what I would do is say, wait a minute, I don't like that. I'm going to go back to this original statement. And in this, I'm just going to put Q sub 4 first and relabel them. Yeah, I'm going to renumber after that. So I'm going to reindex and say that Q sub 4 becomes Q sub 1, and then I shift all the others to the right, right? So just so that this works out, right? So we say I equals 1 after rearranging, i.e., so written again, P sub 1 divides Q sub 1. But Q sub 1's prime, right? So P sub 1 is equal to Q sub 1, since q sub 1 is prime. Okay. So p sub 1 and q sub 1 are equal. So then going back here, I can rewrite this expression as follows. This is some expression m, right, which is, we'll say, n over p sub 1. But if I divide n by p sub 1, well, there's two ways I can do that, right? I can divide this bit by p sub 1, in which case I get p sub 2, p sub 3, on out to p sub r. But at the same time, this right-hand side, since q sub 1 and p sub 1 are equal, this right-hand side, when I divide by p sub 1, I get q sub 2, q sub 3, and so on. Okay. But since m is just n over p sub 1, it is strictly less than n. But by assumption, if these were two different factorizations of n, then after finding p sub 1 and q sub 1 to be the same and dividing by them, what I get is two different factorizations for m, right? So here, but m can be factored in two ways, in two distinct ways. But that's a problem because here it is strictly less than n, but I said n was the smallest such integer that could be factored as a product of primes in two ways. This is a contradiction. Contradiction since n was supposed to be the smallest such integer. Right. Another way that, and in fact, if you've seen this before, you may have seen the reasoning go something like this. So here's just a really slick way of doing it. Another way that's kind of an intuitive way of thinking about proving uniqueness is just continue this process, right? So continue this process. What do you find, right? We saved ourselves the time of trying to use this argument, but continuing this process, right? Okay, I'm at this step. Now what? Well, I can do the same exact thing, right? P sub 2 divides the left-hand side here, right? So it must divide the right-hand side. So P sub 2 divides something, one of these q's. Again, after relabeling, I can assume that it divides q sub 2. But since q is prime, well, then P sub 2 and q sub 2 are equal, and I can divide, and I get more. So you see what the issue is here, right? I can continue to do this until I have divided by all my p's here, right? So it's clear what it is that's going on here, right? Okay. So this is a cleaner way of doing it, though. All right. So we've done it. We have proven, I should say, this little bit is for the uniqueness. Maybe I should draw another one here to say we have shown the truth of the fundamental theorem of arithmetic. Okay, that every integer greater than 1 can be written as a product of primes in a unique way, right, up to the order. Now, of course, when we're going to do this, right, so we are going to use the fundamental theorem of arithmetic. So fundamental theorem of arithmetic. I'll write it like that to not confuse it with fundamental theorem of algebra. So I can express some integer a as 2 to some power, we'll call that a sub 1, 3 to some power, call it a sub 3, sorry, not a sub 1, a sub 2, call this a sub 3, times 5 to some power called a sub 5. So we do this with the subscripts just to keep track of it. It's much, much better than doing that, than having to remember how far I am in the list, right? So if it has, so many copies of 17, I don't need to remember what prime 17 is. Okay, so each of these a sub p's are all non-negative, right? And all but finitely many are 0, right? If that weren't the case, you would have like an infinite product of integers here, and the end result would not itself be an integer. So that's a good thing to remember. So let's say that a is let's say a is like 50, right? So then it's a way of writing this. This is 5 times 10, so that's 5 times 2 times 5. So this is 2 times 5 squared, right? 2 times 25. Okay. So what is using our notation here, right? A sub 2 is 1, and a sub 3 is 0, and a sub 5 is 2, and a sub 7 is 0, and a sub 11 is 0, and so on. And all the rest of them are 0. Okay. Now, of course, this is an extremely, for a lot of things, putting an integer into this form is an amazing thing, right? This is kind of the most convenient possible form that you can put it in. A way to think about that, right, is imagine I ask you to multiply like two gigantic integers in your head, right? Like if I had asked you to multiply, let's say 2 squared times 3 to the 5th times 7 cubed times 11, and I want to multiply that by 3 to the 4th times 5 cubed times 11 squared. These are two pretty huge integers, but multiplying them like this is not so bad, right? This is 2 squared times 3 to the 9th times 5 cubed times 7 cubed times 11 cubed. Right. And as we'll see soon, like this is a gigantic integer. I can quickly multiply this. No special computational tools needed, and it turns out I could actually see a lot of I could basically see a lot of facts about this number just looking at the prime factorization in this way. So for instance, whatever this number is, it's 4 times a cube. Okay, it's 4 times some integer cubed. So there's a lot of things you can do if you have an integer already in this form. Now, it turns out, unfortunately, that taking a gigantic integer and putting it into this form can be a long process if you don't know something else. That can be a hard problem to do. So methods that we use that rely on already knowing the prime factorization for something are not maybe going to be as efficient as I already mentioned. So for instance, even for like finding the GCD, it's not as efficient to use this if you don't already have the prime factorizations in front of you, because if you're talking about doing this for really gigantic numbers, factoring one of them can be really, really hard. It turns out that you can basically get the job done only knowing one of them in that case, but if you don't know either, it's actually quicker to use the Euclidean algorithm. Okay. Anyway, so here's a quick proposition that I'll prove next. So let a and b be positive integers with a factorized is 2 times a sub 2 times 3 times a sub 3 times 5 times a sub 5 and so on, and b factorized is 2 times b sub 2 times 3 times b sub 3, or to the b sub 3, times 5 to the b sub 5. Okay. Okay, so again, same thing. Both of these, all these are non-negative. All but finitely many are 0. Then this gives us a new way of thinking about divisibility. Then A divides B if and only if these exponents satisfy the inequality a sub p is less than or equal to b sub p for all p. Okay, so this is a nice quick characterization. If you have two prime factorizations in front of you, you can essentially read off immediately just by comparing exponents whether or not one divides the other. Okay, so this is a nice fact to have, and it's not too complicated. It's really just some bookkeeping. Okay, so I'll prove this proposition next. Okay, so how do I do this? Let's go in the forward direction here. So if A divides B, then there exists an integer C with AC is equal to B. Okay. Since C is some integer, and we can assume C is a positive integer, what we can get here, of course, if A is not equal to B, then if A were equal to B, we'd be done. So C is greater than 1, so it has a prime factorization, right? So this goes unsaid, but this is why we can do this. So write C is prime factorized as 2 to the C sub 2 times 3 to the C sub 3 times 5 to the C sub 5, and so on. Okay, then if that's the case, I multiply A times C. So A times C is, A was similar except the exponents were A sub 2, A sub 3, A sub 5. So this is 2 to the A sub 2 plus A sub, or C sub 2, sorry, times 3 to the A sub 2 plus, or sorry, A sub 3 plus C sub 3 times 5 to the A sub 5 plus C sub 5, and so on. And that is equal to the expression for B, which was 2 to the B sub 2 times 3 to the B sub 3 times 5 to the B sub 5, and so on. Okay. All right. So by fundamental theorem of arithmetic, what does this mean? So A sub p plus C sub p is equal to B sub p for all p. Is what we get. But when we wrote C as this in its prime factorized form, when you write something in its prime factorized form, what's always true? These exponents are greater than or equal to 0, and only finitely many of them are non-zero. So what that means is that, oh, well, A sub p is less than or equal to b sub p for all p. Since b sub p is some non-negative thing plus some non-negative thing, right? Okay, so that's the forward direction. So then what's the backward direction? Oh. If a sub p is less than or equal to b sub p for all p, define c sub p to be the following. So define this to be b sub p minus a sub p. Since this inequality holds, this is always non-negative. Let c be 2 to the 2 to the c sub 2 times 3 to the c sub 3 times 5 to the c sub 5 and so on. Then a times c is equal to b, thus a divides b. And we're done. Okay, so the book brings up something here that I had mentioned before in this proof and the previous proof, that technically, right, you do have to say, like, when we're talking about defining these products, right, and we have to write them this way because we want to be general and say, you know, the primes, or the thing that we're talking about, could involve primes that are, you know, many exponents down the line, right? These primes could be really far off, and so because of that, you know, all you have to do is just keep track of the fact that, well, okay, all the exponents are greater than or equal to 0, and all but finitely many of them are just 0, because otherwise you'd have an infinite product of things that's that are integers, and so that product itself wouldn't actually be an integer, so you wouldn't be able to do anything. So in this case, multiplying these, you know, things where there might be a worry that there's like infinitely many terms in these products, all you have to say is that everything involved, only finitely many terms are non-zero. So any product of things like that is no big deal. Okay. So further, well, before I write this proposition, I have to make a definition. So definition. We've talked about the GCD already, so there's a thing that pairs with the GCD that you're aware of, which is the LCM, right? The least common multiple. So the least common multiple of numbers A and B, sometimes written with a square bracket. I'm always going to write LCM of A and B, so I'm always just going to write this. Okay, this is defined to be the smallest positive integer that is divisible by both A and B. Okay. All right. So the reason I wanted to define this first before writing out what this next proposition is, these prime factorizations give us a particularly nice way of expressing GCD and LCM. This is really nice if you have the prime factorizations in front of you. Okay, proposition. This proposition, I think, was so going back to my days of undergrad math, I want to say that, like, this was one of the first, like, this is one of the first non-trivial, like, proofs that I had to do in some way that wasn't something like an induction proof. Was the proof of this fact. I don't know why that that stuck with me. But anyway, so let A, it's not hard proof, but let A and B be two positive integers. It looks like I wrote two positive as one word there, like there's some, here, be two positive integers. Let say A is 2, A sub 2 times 3, A sub 3 times 5, A sub 5, and so on, right? The usual. B, same thing. Not even going to annoy you by saying it out. So we have two factorizations there, right? And so let these be the prime factorizations of A and B. That way I don't have to say anything else about what those exponents are doing. Okay, so you already know. All right, let D sub P be defined to be the minimum of A sub P and B sub P, and E sub P defined to be the maximum of A sub P, B sub P. Okay. Then the GCD of AB is 2 to the D sub 2 times 3 to the D sub 3 times 5 to the D sub 5, and so on. And the next thing, the LCM of A and B, is 2 to the E sub 2 times 3 to the E sub 3 times 5 to the E sub 5. Okay. So there is a very nice, simple way of expressing both the GCD and LCM of two numbers in terms of their prime factorizations, where these exponents are either the mins or maxes of the exponents, right, pairwise per prime. So how does one, the first thing that students always say when they see this is, wait, this is the greatest common divisor, but the exponents are the minimum, right, between A sub P and B sub P. And this is the least common multiple, but the exponents are the maximum, right? So that somehow doesn't mesh with me saying greatest, but I'm taking the smallest exponents. And here I'm saying least, but I'm taking the maximum exponents. But of course you know what the deal is here, right? The idea is that if I don't take the smallest exponents here, then this thing's not even guaranteed to be a common divisor of both of them. So the point is that I have to take the min here for this to even make sense. Same thing for the LCM. If I don't take the max here, then this thing is not even guaranteed to be a common multiple of these things. So that's the deal, right? The deal is I want to guarantee that the thing that I get is a common multiple. I just want it to be the smallest common multiple. So in that case, what is this? It's literally you take the max at every step here of these exponents. So showing this is not so bad. So let's show this, and I'll do a couple of examples. So quick proof. Let's let D be any common divisor, and let's say D is 2 to the D sub 2 times 3 to the D sub 3 times 5 to the D sub 5, and so on. Okay, so say that that's its prime factorization. So since D divides A, D sub P is less than or equal to A sub P. for all p. Similarly, since d divides b, d sub p is less than or equal to b sub p for all p. The GCD happens when so the GCD happens when the divisor has each exponent d sub p as large as possible. So it turns out what's important here is this is going to be as large as possible when it's not necessarily the as large that matters here. It's the as large as possible here. So when does this happen? This happens when d sub p is equal to the minimum of a sub p and b sub p. That does it, right? Oh, I was almost off screen. Okay. So similarly, what do I get in the other case? So similarly, let E be any common multiple of A and B with, let's go ahead and say that E is expressible using its prime factorization as 2 to the E sub 2 times 3 to the E sub 3 times 5 to the E sub 5 and so on. Well, A and B both divide E. So what does that mean? It means that A sub p and b sub p are both less than or equal to E sub p for all p. Right. So the LCM happens when the multiple is or I should say it happens when the E sub p, it's true, I mean, it's what I had here is totally fine. It happens when the multiple is as small as possible, but that is when the E sub p is as small as possible, and I'm running out of room. i.e., E sub p is the max of A sub p, B sub p. Again, don't focus on the as small things. Focus on what you need to actually make this work. Okay. So this is nice. In fact, here's a quick example. So A, we'll say is 720, and B is 6300. So 720 I can factor as 2 to the 4th times 3 squared times 5, and 6300 I can factor as 2 squared times 3 squared times 5 squared times 7. Okay. Alright, so there's my two integers. Then note that d sub 2 is, so d sub 2 is the min of these two, so it's 2, and d sub 3 is the min of these two, so that's also 2. D sub 5 is 1, and d sub 7 is 0, right? So to see that d sub 7 is 0, of course, here's power of 7. Oh, but of course there's a smaller power of 7 showing up there. I just don't write it, right, to save myself hassle. Okay. Thus, GCD of 720 and 6300 is what? So it's 2 to the d sub 2, so that's 2 squared times 3 squared times 5 to the first times 7 to the 0, and then I don't write out any of the other 0 exponents. So this is 2 squared times 3 squared times 5, so that's 180. Okay, so that's a quick way of doing it, right? Okay. Similarly, you could compute the LCM here. This is, again, like a really nice way of going about it, so long as you have one or both. So why do I say one or both of the factorizations? So if you know the factorizations of at least one of them, what you could do is you can just test you can test every single one of the prime factors showing up in the one you know and see if it will divide B, right? Because the prime factors of A are the only ones that can actually occur in the GCD, so it doesn't matter which one you can factor completely as long as you can factor one of them. So if you can factor one of them, right, the only prime divisors that can show up would be, you know, potential prime factors of one of them. So you don't actually have to have both of them factored to get this done. But the problem is even just having one factored. So you would use the Euclidean algorithm if you didn't, if you wanted a quick way of doing it and didn't know anything else. Okay. Quick definition so that I can state and prove this last proposition in this chapter. So a positive integer n is square free, okay, if all of the factors that occur in its prime factorization why did I put an E on occur? So positive integer n is square free if all the factors that occur in its prime factorization are distinct. Okay. So i.e. n is not divisible by any square greater than 1. Okay. So quick example here. So 165 is square free. And the reason why it's square free is if I write out its prime factorization. Prime factorization of 165 is 3 times 5 times 11. So I can just see, right, that none of these have power 2 or greater. So that's it, right? So what this is saying is that in your list, in your prime factorization, you don't have copies of the same prime showing up, because the second you do, then you are divisible by some square that's bigger than 1. So 585 is not square free. And to see this, note that 585 is 3 squared times 5 times 13. Okay. So 3 squared, for instance, divides 585. So it is divisible by a square that's bigger than 1, so it's not square free. Okay. Alright, so this just gives us another way of classifying divisibility properties of numbers. So this is what it means for an integer to be square free. Okay, so the reason that is important is the following. I wanted to say that before I could state this theorem, and it makes sense. I guess I should call this proposition. It's not super important or anything. So let n be a positive integer. Then there is an integer r that is greater than or equal to 1 and a square free integer s that is greater than or equal to 1, such that n can be factored as r squared times s. What does that mean? So think about what that means. So if you have a positive integer, then it's possible that it's square free, also possible that it's not. If it is square free, of course you could take r equals 1 here, and n is equal to 1 squared times s, and you have this factorization. If your n is not square free, what this is saying is that you could factor this in a way that is some integer r squared times a square free integer. Meaning, if you took that in and divided by this r squared, you would get a square free integer. Okay, that's what this is saying. Okay, so proof. This isn't too complicated. So let n equal some. Let it have its prime factorization. P sub 1, a sub 1, p sub 2, a sub 2, and so on. So p sub k, a sub k be the prime factorization. Okay. So if a sub I is even, right, a sub I is 2 times b sub I for some integer b. And if a sub I is odd, right, a sub I equals 2 b sub I plus 1. Okay. So let r be p sub 1, b sub 1, p sub 2, b sub 2, and so on, all the way up to p sub k, b sub to the b sub k. Okay. And let s be the product of the primes p sub I for which a sub I is odd. Okay, then what is r squared times s? This is p sub 1 to the 2 b sub 1 times p sub 2 to the 2 b sub 2 times all these out to the p sub k 2 b sub k times s but that's just everything. This is just p sub 1 to the a sub 1, p sub 2 to the a sub 2, and so on. P sub k to the a sub k, that's just n. So that's it. Okay, so nothing really other than just some bookkeeping. Okay. Okay. So it can be a little, it might be a little confusing here when you look at this and say that as the product of the primes for which a sub I is odd here. And of course, you know, they don't, if none of them is odd, then you can just set s equal to 1. That's fine. That's fine too. Well, why is that fine too? This is something I didn't address when I wrote down the definition. So the question is 1 square free? And we say, yeah, 1 is square free. Okay, so if 1 is square free, then s being equal to 1 is fine here. So I should have mentioned that before, that 1 is an example of a square free integer. So so s being 1 is fine here. What this is really saying is that s is only taking care of I said odd here, but of course the way that this is defined, s is only really taking care of primes to the power of 1 here. So yeah, I like phrased it as each of these a sub i's is it's the product of the primes for which the a sub I is odd, but what the s is taking care of then is just it's the plus 1, right? It's taking care of the single powers of primes. So to see that like in an example, so here's one straight from the textbook. So n is 2 to the 5th times 3 squared times 7 cubed times 17. Then what is r? So r is 2 squared times 3 times 7, and s is 2 times 7 times 17. Right. So note, I square r, I get 2 to the 4th, 3 squared, 7 squared, and then s takes care of the single powers that weren't covered by squaring r. So I get an extra copy of 2. Here I would only get 2 to the 4th, so I get a 2 to the 1st here. Here I get 3 squared, so I don't need any powers of 3 showing up. Here I would only get 7 squared, so I need an extra copy of 7. Here 17 didn't show up, so I get 17 slapped on. Okay, so that's how that goes. All right. So all of these things were, all these things that follow that fundamental theorem of arithmetic were applications of fundamental theorem of arithmetic. And we're going to do this throughout the rest of the course. You're going to see plenty of applications of fundamental theorem of arithmetic, which of course itself was really, after tracing it back, was just an extended application of the Euclidean algorithm, or specifically the fact that you could use a Euclidean algorithm to write out the GCD as a linear combination of A and B. Okay, so now I want to, there's an entire chapter that is dedicated to applying this fundamental theorem of arithmetic. So the first application, I'm going to mention a puzzle. So this is 5.1. Here's puzzle. It says there was a young lady named Chris who, when asked her age, answered this: 2/3 of its square is a cube, I declare. Now what was the age of the miss? So this is a limerick problem. So we're told, young lady, what is her age? 2/3 of its square is a cube. And that should be enough to tell us. So you'll see why the word young matters here in a second. So so this is chapter 5.1, puzzle. So let A be her age. These problems stated as age problems are a classic in number theory. Even Diophantine equations are named after Diophantus, and supposedly on his tombstone had a riddle about his age that I might assign you as homework. Oh, by the way, yeah, homework 2 I'll assign later today, and it'll be due on Thursday. Your exam, instead of giving it to you on Thursday and having it due Friday, I think what I'm going to do is just assign it to you Friday and have it due the following Monday. And I'll do that for the second exam as well. The final exam will be due on the day. I'm not going to have you working past the class or anything. So the final exam will be different. It'll be given to you like the day before or a couple days before. But the next exam I'll give you this Friday, and then you'll have the weekend to work on it. Okay, so let A be her age, and I mean her age is a positive integer, so we will write it as its prime factorization, so 2 to the A times 3 to the B times 5 to the C times 7 to the D, and so on. Okay. All right, so that's prime factorization. So then 2/3 times A is, well, in terms of prime factorization, I can write this in a particular way, right? This is 2/3 times that prime factorization. So writing it like this is 2 times 2A is what? So 2 times 2A is, well, it's 2/3 of the square that I'm really concerned with, right? I need to remind myself what the puzzle was even saying. So 2/3 of its square is a cube. Okay, so it's not just 2/3 A. So it's 2/3 square, 2/3 A squared. So 2/3 A squared. So A squared, then, well, that's easy enough to compute. A squared is just 2 to the 2A times 3 to the 2B times 5 to the 2C and times 7 to the 2D, and so on. Okay, so that is not too bad. So what do I say here? So now 2 times A squared is going to be an extra copy of 2, so that's 2 to the 2A plus 1, and I'm dividing by 3, so I get one less copy of B, so this is times 3 to the 2B minus 1, and nothing happens with the other primes. So this is 5 to the 2C times 7 to the 2D, and so on. Okay. Well, that's what I have. Don't really know what to make of that yet. So supposedly this is equal to a cube, right? And then this is equal to some cube. But how would that help us? Well, in order to see how this would help us, I need another fact. So a quick proposition is the following. Let k be an integer bigger than or equal to 2. And let m be a positive integer. Okay, then m is a kth power if and only if all the exponents in the prime factorization of m are multiples of k. Ah, so that's really nice because this places a strong restriction on the prime factorization itself. So looking at a number's prime factorization can immediately tell how that number can be expressed, or whether that number can be expressed, as a cube, right, or a fourth power, or as a square, right? It's a nice fact. Okay, so let's prove this thing. I think I have just enough time to prove this and then apply what I know here. So let m be 2 to the y sub 2 times 3 to the y sub 3 times 5 to the y sub 5, and so on. Okay, if each y sub p is a multiple of k, then y sub p is equal to, say, k times z sub p for some, well, first of all, for all p, but for some integer z sub p. Okay. Thus, m is, I can just directly write it as 2 to the z sub 2 times 3 to the z sub 2, or z sub 3 times 5 to the z sub 5, and so on. If I raise that to the k, then that's exactly, I just get m, right? So all right. So I can express m as a kth power just directly, knowing that each of its exponents in its prime factorization is a multiple of k. So on the other hand, conversely, if m is equal to nk, let n equal 2w sub 2 times 3w sub 3 times 5w sub 5, and so on, be its prime factorization, so be prime factorization of n. Then two to the y sub 2 times 3 to the y sub 3 times 5 to the y sub 5, and so on. This is m, which is n to the k, which is 2 to the k times w sub 2 times 3 to the k times w sub 3 times 5 to the k times w sub 5, and so on. And that does it, right? So y sub p is equal to k w sub p, right, for all p. And we're done. Why can I say this? Why can I say that this means the exponents are equal? This comes from the uniqueness, right? This is the application of the uniqueness of this factorization. That's why this works, and so this is actually a multiple of k for every prime. So every single one of those exponents is a multiple of k. And I'm done. So I will use this fact at the beginning of class next time to solve this puzzle. And we'll proceed from there. So the rest of chapter 5 is going to be nothing but applications of fundamental theorem of arithmetic. And that's going to it's going to get us a bunch of stuff. It's going to get us rational root theorem. It's going to get us some facts about Pythagorean triples that are really nice. And like your first example of something that I hope to get to by the end of the course. It's really cool. But anyway, this is so I think think that's more or less it. I'm going to clean up the syllabus page and post all of the previous lecture videos under the actual like lecture schedule, so that the lecture schedule includes what was covered that day as well as the YouTube video itself. So I'm going to edit that, and I may remove last Friday's office hours just because there's only a couple questions asked, so I don't want people to waste their time like clicking through like a 2-hour video to try to find something. I guess the best thing is and next time what I'll do, I'll either add timestamps, or I will always start with a fresh sheet so that you can tell when I start writing that like I'm actually solving a problem by hand. Or you can pay attention to the chat as well, because I answer a lot of questions in chat too when they're asked. So anyway, I think that's it for today. So same time tomorrow. Like I said, your second homework will be posted later today, here in like a couple hours.